We are going to do 4 examples today. This will carry you through the worksheet. I have to have a e-learning assignment for you. Your e-learning assignment is the thing you have in front of you right now. You had time to work on that yesterday, obviously, right? Your worksheet. Know your worksheet? Aye, aye. You want to go back to SOHCAHTOA? Yeah. Yeah. For some, it's really confusing. So yeah. Here we go. Here we go. Here we go. Let's look at 3 integrals that are a little bit more challenging. So this is a review of not an indefinite integral, but of a definite integral. We will come up with an answer. We will come up with a numerical result. But I want to see who has an idea of how I should handle this whole 1 minus the cubed root of x over the square root of x. What's that? Bring the root of x up top. Okay. And what are you going to do with it when you put it up top? Okay, so Rachel's got a great idea, and I'm going to write it just slightly differently than how she chose to do it, but 1 minus the cubed root of x, or x to the 1/3, and then what she did is she brought that square root of x up top, so it was x to the negative 1/2. And actually, you know what? We'll just go ahead and we'll treat it just like Rachel decided to do it, okay? And I'll save my idea for when we're down here, okay? All right, so now that I have it like that, I can distribute that x to the negative 1/2, and I get x to the negative 1/2 minus, what do I do when I have negative x to 1/3 times x to the negative 1/2? What do I do to the exponents? I add them. And 1/3 added to negative 1/2, that'll be like 2/6 plus negative 3/6 is negative 1/6. So x to the negative 1/6. So I could rewrite this as the integral from 1 to 2 of x to the negative 1/2 minus x to the negative 1/6 dx. Antiderivative of x to the negative 1/2. I increase the exponent by 1, and I divide by the new exponent. So it's x to the 1/2 divided by 1/2, which is the same as multiplying by. So I have 2 roots of x minus, what do I get if I take negative 1/6 and increase that by 1? 5/6. So x to the 5/6 divided by 5/6, or multiplied by 6/5. And I'm going to evaluate that here and here. So I plug in 2. And, you know, I didn't really make the exponent. The point of this problem is really to go through and, you know, find the antiderivative. So I would plug it in now. No nice way about going over this. We would have 2 roots of 2 minus, what is 2 to the 5th? 32. So we'd have 6 times the 6th root of 32 over 5 minus, and then we plug in 1. If we plug in 1, what would you get? 2 minus 6/5. And we could just plug that in and, you know, come up with some decimal in our calculator, right? Okay, so we'll leave it as that for right now. How about h? How would you go about finding the antiderivative here? I got to rewrite this one as well, don't I? How would you rewrite this? 4y minus 3 to the 3y to the negative 2. Okay, so I've got the integral negative 3, negative 1 of 4y minus 3y to the negative 2 dy. What's the antiderivative of 4y? 2y squared. Good. And what? Plus 3 over y. Good. Plus 3 over y. I'll plug in the negative 1. What do I get? Dose, very good. Minus 3. Yeah, that works out pretty well, huh? Minus 18. Minus 1. That looks pretty good there, huh? Negative 1 minus 17 is negative 18. What does that mean about the curve? That it sits below the x-axis, right? Now, let's also just look at one more thing here to consider. True or false? This function is defined for all real numbers. False. Where's this function undefined? 0. Do I cross over 0? No. So the fundamental theorem of calculus does apply, but if I crossed over 0, then we would say fundamental theorem of calculus does not apply because it would be undefined at that spot. Okay. Okay, did you guys find an antiderivative? No? Huh. Well, I'm going to rewrite it. I'm going to divide each part, each numerator, I'm going to divide by sine squared. I'm going to rewrite it. So, for example, if I had 4 plus 5 over 3, does everybody agree that that's 4/3 plus 5/3? You agree that those expressions are the same? So that's the property I'm going to use here. It's very, very useful when you're going through integrals. What is 1 over sine squared? What's 1 over sine? Cosecant. Good. Cosecant squared. And then I have sine squared over sine squared, which is 1. So we know the antiderivative of 1. The antiderivative of 1, super easy, right? Huh? What? Yeah, exactly. The antiderivative of 1 is theta. Do you know the antiderivative cosecant squared? Very good. Riker is correct. This is one we should have committed to memory. The antiderivative cosecant squared is negative cotangent squared. Bailey's got a thing. Definitely not. Nope. Nope. So so when you say that you're going to use one of the signs there and one of the signs there, you're splitting up as though you're multiplying two things. So if you want to do that, here's how you'd have to write it. You'd have to write it 1 over sine of theta times 1 plus sine squared of theta over sine of theta. And that actually doesn't really do much to help us at all, does it? So what I did is I rewrote it not by multiplication, but by using addition. I just rewrote the two fractions. Excellent. We have cotangent squared of theta. What's the cotangent of pi over 4? Oh, wow. Yes, it is 1. Let's see how Sydney did that, okay? So pi over 4 has this terminal point, root of 2 over 2, root of 2 over 2. Tangent is what? Y, x, x over y over x. What is tangent? Is y over x. So if you take y over x, you get cotangent is the reciprocal. What's the reciprocal of 1? Squared, make it negative. Look at that, negative 1. Plus, we plug in pi over 4 for theta and you get? What? Pi over 4, right? So we've got negative 1 plus pi over 4, and then we minus, now we plug in 0. Cotangent of 0. What's that coordinate? It is 1, 0, right? So tangent is y divided by x. What's y divided by x? So what's cotangent then? Oh, no. Oh, no. Why? Why does the fundamental theorem of calculus part 2 not apply? How could we have seen that right at the very beginning, folks? Where is sine equal to 0? At 0. And do we cover 0? Yes. So it is undefined on the interval. So I wanted to show you this problem for two reasons. Number one, finding the antiderivative the way I did is a very useful technique. But also, you can see that sometimes you come up with that result. If you look back at the beginning, you can see Fundamental Theorem Calculus Part 2 does not apply. And still very useful to find this antiderivative. That's why I had us go through the problem. But you can see what happens when you come across a spot that causes an issue. What would you do for the last one? I like that idea. We're going to go with Maya's idea. We got pi over 3, pi over 6. And we're going to change cotangent to what? Cosine of theta over sine of theta times sine of theta over 1 d theta. What happens? They cancel. So what's the antiderivative of cosine? Sine of theta. Is it positive sine or is it negative sine? Are you sure? Here's how you check. You look at your answer. What's the derivative of sine? Cosine, which is what you want. There we go. Hey, you. So I evaluate sine of theta at pi over 3 and pi over 6. So at pi over 3, what is my terminal point at 60 degrees? And at 30 degrees, it is sine the x value or the y value? Sine is the y value. So therefore, you have the root of 3 over 2 minus 1/2, which is the root of 3 minus 1 all over 2. So why do I put some of these examples here? Folks, we're not allowed to forget our trig. And I know that seems challenging because I know that for a lot of us, the trig has kind of left our brain. As you can see, I do try to bring it in a little bit more and more all the time so you can see it. It is something that we want to be able to deal with. So lots of trig examples on that side. You're now ready to complete the rest of your assignment. And we will be moving on Tuesday. We'll be moving on Tuesday.